All right, in this last video of Chapter 6, Section 7.6, we'll look at some general trends of groups and families on the periodic table. First, we're going to look at the difference between some metals, nonmetals, and metalloids. And if you have your periodic table handy, you can make sure that you know the difference between those. You can notice that the nonmetals are mostly over here, labeled here in kind of a greenish color. And then the semi-metals kind of make that purplish color right here, and everything else is a metal except for hydrogen. So here's some general pieces about metals and nonmetals. Generally, metals are shiny. They have a shiny luster to them. They're malleable, meaning that you can hammer them into different shapes, and ductile, meaning you can draw them into wires. They're good conductors of electricity, which is a physical property. And their metal oxides are basic when put in solution. Nonmetals are dull as opposed to shiny. They are brittle as opposed to malleable and ductile. They're insulators, not good conductors. And the nonmetal oxides are acidic versus the metal oxides, which are basic. These generally form cations in solution, the metals do, and nonmetals form anions. And so these guys form positive things, these things form negative type things. So we've probably drawn this on your periodic table a number of times, but the nonmetals are mostly over here, the metals are mostly over here, and then remember hydrogen is an exception and is one of the nonmetals there as well. And this little group down here, these guys, these lanthanide and actinides, remember fit in here, and those are also metals. So here's a couple of the trends that you might not know as far as chemical equation goes. A metal oxide forms a base. So metal oxide and water forms a basic solution that generally has OH in it, a hydroxide group, meaning that it's basic. And so here is a metal oxide, metal being sodium oxide. React it with water, and it makes a base, NaOH, a strong base, not O. A nonmetal oxide makes an acid. And so nonmetal oxides would be these guys over here with oxygen, and then they react with water, and they form an acid. In other words, something that starts with an H. And a good example of that would be carbon dioxide. Carbon dioxide is a nonmetal, carbon and oxygen. React that with water, and what do you get? Well, you get carbonic acid, H2CO3. This actually gives you the sharp taste to your soda pop or your bubbly water when you drink it, because it is acidic, because it has carbon dioxide gas in it. Next, we'll take a look at the metalloids a little bit, and then we'll look at the trends on the periodic table. So the metalloids generally just have mixed properties. Excuse me, I'll move this page of notes. Mixed properties, and so they'll be shiny, maybe like a metal, like this, but then they'll also be semi-conductibles or semiconductors. Silicon is an excellent example of that because it's one that looks like a metal, and yet it only sort of conducts electricity, and so it's sort of an insulator as well. So they can be kind of a mix of both. All right, let's zoom in at the section 7.7, some trends for the group 1 metals and the group 2 metals. So group 1 is called the alkali metals right here, and I've got them listed right here: lithium, sodium, potassium, rubidium, and cesium. And they're all shiny metals that are actually soft. You can actually cut them with a knife. You can see this is sodium right here, and it's being cut with a knife. But they're very reactive, and as a matter of fact, they become more reactive as you go down the group of the family. This can be explained by their atomic size, and so the electrons are further away from the nucleus in cesium than they are with lithium, and so they become more reactive as they go down. You can see that the melting points also decrease as you go down. Cesium will actually almost be a liquid at room temperature, and then they get more dense as they go down as well, and of course their atomic radius increases, as we just talked about, which leads to more reactivity. And you can see the really low ionization energy here of cesium versus the little bit higher ionization energy of lithium. They have characteristic flame color tests. So if you take each one of these elements and place it into a flame, you can see that they give a characteristic color because their electrons are excited by the energy from the flame, and then they give off a wavelength of light that happens to be one that you can see that's colorful. Potassium and lithium are, potassium is kind of a lilac colored flame, sodium is kind of a yellowish colored flame, and then lithium is a reddish colored flame. Let's look at the second group, second period. So these are the alkali earth metals, beryllium, magnesium, calcium, strontium, and barium. They once again are also more reactive. They all have the electron configuration of S2 going down them, so 2 electrons in the outer shell, and then in their valence shell. You can see the melting points become less as well because the electrons become further away from the nucleus. Their density increases and their atomic radius, of course, gets larger, which leads to them becoming more reactive. So barium is much more reactive than beryllium, just because its electrons are further away from its nucleus. All right, let's finish with a few trends for some nonmetals on the periodic table. The first nonmetal we're going to look at is one called hydrogen. Hydrogen is a super special element on the periodic table. Hydrogen is the only element whose noble gas does not have an octet. And so the noble gas in period 1 is helium. And so hydrogen with 1 proton and 1 electron, to become stable, wants to get to have 2 electrons. And so it forms the stability with only 2 electrons. That's why it only forms 1 bond ever, because hydrogen forming 1 bond that shares another electron with something will have 2 electrons, and therefore it will have achieved a stable noble gas configuration. So hydrogen forms a lot of what are called shared electron bonds, and the fancy name for shared electron bonds are molecular or covalent with nonmetals. That's why you see hydrogen being the thing that makes things are acids like HF or HBr. These are nonmetals, and hydrogen forms a bond with them that's called a covalent or a shared electron bond. Hydrogen, special element. We'll finish with 2 other groups of nonmetals. Let's look at the oxygen group. The oxygen group, of course, right here has a generally -2 charge, but not always. It has 6 valence electrons. And if we look at their setup right here, you can see an 2s2p4, s2p4, S2p4, S2p4. Now I know they have some d orbital electrons there and maybe even some f's in here, but it's the s and the p electrons that we look at for its reactivity. You can see that the melting point greatly increases as you go down the group of the family. You can see oxygen's a gas at room temperature, but then sulfur is a solid. Densities increase as well, and the atomic radius increases as well. And then their ionization energy, of course, decreases because the atomic radius increases, making the electrons be further away. A couple of interesting pieces are that there are 3 allotropic forms of oxygen. There's just monatomic oxygen, which doesn't really exist in nature very much. There's O2. This is the elemental form. This is the one we see here on Earth a lot. And then there's O3. This is called ozone. This is the one that's up in the higher layers of the atmosphere. Sulfur actually exists as S8 in its elemental form, a ring of 8 sulfurs stuck together, making it really stable, but it's the most common form that you see. So the general rule for those guys is that they'll form -2 ions, and they'll want to share 2 electrons with something else to obtain a noble gas configuration. Last groups, Group 7 and Group 8. So Group 7 are the halogens. Halogens information is right here, and you can see that they're all diatomic, fluorine, chlorine, bromine, and iodine. Bromine's a liquid at 25 degrees Celsius, so it's one of 2 elements on the periodic table that's a liquid at room temperature in its elemental form. Iodine's a solid, and then these 2 are gases right here. You can see that the atomic radius, of course, increases, and therefore the ionization energy decreases because the electrons are further away in iodine's atomic radius than fluorine's. Last ones are the noble gases. And the noble gases, well, they're noble. They have all full electron shells. They're monatomic gases, meaning they don't exist in pairs, and they're mostly inert. We'll see a few times where krypton and xenon form a few compounds, but it's fairly rare. And you can see some of the same pieces right here. Helium is one of the lowest boiling points on the planet. Super cold before you can actually get it to be liquid helium. And then you can see that xenon, we're getting there with xenon. You could actually have liquefied xenon at 165 Kelvin. A little bit warmer, but still quite chilly. Notice they all have full electron configurations, and so they're kind of the standard that offers stability for all other atoms on the periodic table. All right, thanks for tuning in. Good luck with your trends on the periodic table.